Greetings. Since rational functions are in the format of ratio, numerator over denominator, where numerator and denominators are polynomial, so polynomial will be a fundamental concept to talk about. Now, in this lecture, I'm going to discuss that subject of polynomial, where it comes from, and where it's going to lead us. And in the next lecture, I will be concentrating on rational functions and their possible graph. Okay, then let's get started, shall we? Polynomials are algebraic expressions in the form of, I have written for you so that you can see it better. In the form of an x to the n plus an x to the n an minus 1 x to the n minus 1, and so on and so forth, and until the last term that is going to be constant. Now, an are numbers. By numbers can be real or complex. And n, which is called degree or power of the polynomial, is an non-negative integer. Could be 0 or 1, 2, 3, and so on. And an and an minus 1, for example, an minus 1 indicates that this coefficient is going to be this particular term, particular x of this term. Now, the first one is called leading coefficient. And naturally, the leading constant cannot be 0. Because if the leading constant is 0, then this term cannot be what the leading term. The next one, if the coefficient of that is not 0, that will be possibly the leading term. That is in case if you have written them into descending order. Now, since addition is commutative, so there is no need to write them like that, because we can flip them over. So, but it is a good practice and better discipline to write them in descending order as far as the power of the x is concerned. Again, you do not have to do it, but again, it will be more disciplined to do that. So the one that is has the highest power, the x has the highest power, the degree we call it is larger. That is called leading term, and the corresponding number before that is called leading coefficient. I'm repeating myself. Okay, now in this definition, I said that polynomial is an algebraic expression. Now, first we have to know what algebraic expression is, so that we can fully comprehend the polynomial. But every algebraic expression, every polynomial is an algebraic expression, but the converse is not true. Meaning that every algebraic expression is not necessarily what polynomial. Okay, now let me see what algebraic expression is. Excuse me. Now, algebraic expression is, I have written for, if you like to take notes. Algebraic expression is if you have a bunch of loose, let's say constant numbers, 1, 2, 3, 7, 15, pi, whatever. If you have a bunch of variables and you glue them together using addition, subtraction, multiplication, division, and extraction of root, which means raising to the power of fraction, any term. That expression that you get by doing that is called algebraic expression. That's simple, huh? Now, I have written that for you. Let me make some examples. You can see that what I mean, what I just said by example. Now, number 3, for example, is an algebraic expression because satisfies the definition I just said. You can put the variable to be x to the 0. And x plus 1 is, x plus y. I'm gluing two variables together. This is an algebraic expression. Same is true if I multiply x times y times z, or divide. And all of them are algebraic expressions. So also taking roots. This means raising this radical into the power of 1/5 in this case. This is an algebraic expression, and so on and so forth. Now the question comes is, what kind of expression are not algebraic? If we know what is not algebraic, we appreciate what is algebraic better. Now, e to the x, that some of you are familiar with, log base bx, all the trigs, sine x, cosine x, tangent x, cotangent x, and their inverses, all these are examples of non-algebraic, which means we cannot get constant and variables and glue them together and obtain e to the x out of it, or obtain log out of it, or obtain sine of x out of it. So they are not algebraic. Okay, so we know what algebraic expressions are. Now every polynomial is an algebraic expression, but the converse is not true. Oh, by the way, let me also have another example which is good to bring. I'm glad I have written them, otherwise I would have forgotten. And that is, now you see there are 1, 2, 3, 4, 5 terms here. The first 4 terms represent algebraic expression. But the last one, e to the x, is not algebraic. Therefore, the entire expression will become not algebraic expression because one of the terms is not. You follow me? Okay. So we know what is algebraic expression and what it is not algebraic expression. Now, going back to the polynomial. Polynomial, as I already defined it, is an algebraic expression because you can have a bunch of constant and variable, glue them together, and this expression comes out of it. Now, this is called a polynomial expression. It's an algebraic expression. If you set it equal to 0, it is called polynomial equation. And if you make a function out of it, it's called polynomial function. Now, the difference between polynomial equation and polynomial function is that polynomial equation has the set of solution of that is finite. The cardinality of the set of solution, cardinality means number of elements that the set has, is finite. For example, if the degree of the polynomial is 7, then you will have 7 solutions. Some of them could be the same, but some of them could be repetition, in fact. And when you have dealing with polynomial equation. Whereas polynomial function, then when you go to the definition of function, which means domain and range, and you're talking about ordered pairs, and the set of ordered pair, which is a relation, will be infinite. So this will have infinite number. The cardinality of the set of this one is infinite. The cardinality of the set of solution of that is finite. Okay, then I don't have to talk about domain and range and function. I have uploaded about 2 or 3 lectures about function and relation, and I will provide you with the site link of it in the comment section to go over that. So I'm not going, that is a long lecture to talk about. So now let's see what the subject is about rational what? Rational function. So let's see what rational expression is. Now, when we define rational numbers, we say rational numbers are those real numbers that they can be written in the form of a and over b, where a and b are integers. and b naturally cannot be 0, the denominator. Integers. So the real numbers is what is limited, pushed into integers. In contrast, very similar to that, we can define rational expressions. So rational expressions are in the form of numerator over denominator, in the form of ratio, but the numerator and denominator are polynomials. So polynomials to the rational expressions is integers to the definition of rational numbers. A very nice correlation, isn't that right? And then if we have rational expression and we make a function out of it, write it in form of f of x equal to that, then we have rational function. That's all there is into that. Okay, now, so rational function, I have written, if you want to write it, is what? Is those functions that are written in the form of polynomial over polynomial. Again, I'm putting that quickly because I've already talked about that. All right, now, this one I've already talked about, rational function. Now, let's talk about rational function, about the relation of the degree of the polynomial in the numerator and degree of the polynomial in the denominator. What role do they play? Now, again, rational function or function in the form of fraction, numerator is polynomial, denominator is polynomial. No, the degree of the polynomial numerator and the degree of the polynomial in the denominator, they play very important role in rational function as far as the graph is concerned. And because in rational function we are dealing with function, and with the word function always goes domain and range, and domain is what? The set of all permissible values that the independent variable can possess. So we come to see what cannot be permitted to be, we extract that one out of domain, but that point that cannot be, which makes the denominator what? Denominator 0, that point play very important, crucial role into the subject of analyzing the asymptote and analyzing and conceptually understanding the graph of the rational functions. Okay, now the degree of the polynomial numerator and degree of the polynomial of the denominator are either equal or one of them is smaller than the other one. And that relation between the degrees of the numerator and denominator, I am repeating myself, has an important role in graphing rational functions that we will be seeing in the next lecture. Okay. This lecture, again, I'm repeating myself, is going to be a preliminary, kind of preparing you. Now, this one I have already discussed it. Okay, then that's all really we need to know for the next lecture. Only last thing I would like to say is that the numbers, again, this is going to be important in rational expression when we discuss it, and I'm going to talk about it again in the lecture. But again, this is preliminary, so kind of prepare you for that. And the numbers between 0 and 1, they behave very, and the numbers bigger than 1, they behave very opposite to one another. The numbers between 0 and 1, if you raise to the power 2, 3, whatever, if you raise it to the power, then the result is smaller than the number itself. So if you iterate, for example, right, raise it to the power of 2, then raise that one, the result of that to the power of 2 again, which means the first one you are raising to the power of 4. Then raising that one to the power of 2 again, which means the first one you are raising to the power of 8, and so on and so forth. You are iterating, and by doing that, you will see that, try with your calculator, you will see that the number is approaching 0, and finally your calculator will give you 0. Now, on the other hand, if you raise to the power of fraction, if you raise it to the, for example, a square root of that. Let's say you take a square root of a number between 0 and 1, then iterate that one. Take a square root of that again, take a square root of the result again, and so on and so forth. It starts to get larger and approaches 1. Isn't that interesting? And the numbers bigger than 1, they do exactly opposite. As you raise it to the power, they get larger. And as you take a square root, as you keep taking a square root, iterate that one, finally you reach to 1 as a limit to the 1. I use the word limit, I will be using as a ordinary conversation, the meaning as a literal meaning of that. I'm not making any delta epsilon definition of limit in the calculus. So this word also you will be hearing when I go over the rational functions. Okay, so this is again important because we are going to analyze the graph of a rational function. Okay, this one I have written, and so why not to put this one up if you like to take a note. This is important. And again, preparation, this is a preliminary. A square root of x, as I have already said, if x is between 0 and 1, then a square root of x is bigger than x. A square root of any number between 0 and 1, bigger than that number between 0 and 1. And I made an example for you. And the same is true with what? With if a number is larger than 1. It's exactly opposite. I have already mentioned, I'm just showing to you in general. So a square root of x is smaller than x if x is bigger than 1. And as you can see, a square root of 4 is what is smaller than 4. And as you can see, 2 is less than 4. And the number that is bigger than 1, you know it naturally, when you raise it to the power, it gets bigger. 2 to the 2 is bigger than 2. 4 is bigger than 2. Okay, then I have put also this one also in chart for, data collection is very important. I always encourage my students to do that. And here, as you can see, I'm selecting numbers between 0 and 1 and numbers between bigger than 1. Now, these numbers are between 0 and 1, 0.5, 0.25, 0.1, 0.01, and so on. As you notice, when you square that 0.25 is smaller than 0.5. 0.063, which is a square of 0.25, is smaller than 0.25, and so on and so forth. And when you take a square root of that, you notice it's larger. 0.71 is larger than 0.5. And 0.5 is larger than 0.25, and so on and so forth. And this table also shows that if the x is bigger than 1, for example, is 1.25, when you square it, this square is bigger than 1.5. It's 1.56. But when you take a square root of that, as you notice, is 1.1, which is smaller than 1.25. It's very good observation to make it, especially for beginner students, when we start to analyze the graph, so that when we say x, for example, approaches 0, approaches some number that is not in the domain, and see how the value of the y will behave, how large that may become, or how it does approach to certain number. Okay, then I thank you for the opportunity, and I hope this lecture was beneficial. I wish you all prosperity, and please stay safe. Thank you, and have a great day. So long.